Hi everyone, this is the continuation of the chapter on graph neural network, graph representation learning. So far we have seen different types of graph representation learning methods, GRL methods. We started off with normal, simple matrix factorization type approaches, and then we looked at more of a random walk kind of approaches where we capture the context using random walk, right? And the problem, we also understood that when the graph evolves over time and there is no learning as such. I mean, in the sense, like, say for example, if the two nodes are very far from each other and they do not share any neighbors, you may not be able to map those two nodes in the same embedding space near to each other on the embedding space, right? So therefore we have looked at, in the last lecture we have looked at some deep learning based methods, particularly the convolutional neural network types methods for graph learning. A quick recap. So last class we have seen that basically it is a message passing, a graph convolutional network, GCN, is a message passing paradigm where for every node you basically receive messages from its neighbors, one hop neighbors, two hop neighbors gradually, and then and this number of hops from which you want to receive messages, that is also a kind of hyperparameter that you choose, right? But generally we do not go beyond 2 to 3 hops. And then say for example, this figure we have seen that let's say we take information from 2 hops, right? So you basically have 2 layers, right? So this is one layer, this is another layer, right? And at every layer there are 2 operations happening. So one is an aggregation operation, which is just an addition, for example, and then some sort of non-linearity. Okay, and here these 2 parameters W and B. So W basically controls, W is a projection of the embeddings of the messages, whatever embeddings, aggregated embeddings coming from the neighbors, and B is the projection of the embedding of the embedding of the node, right, at the previous timestamp, right, at the previous hop, for example. Okay, and then what we do for every node, we build this computation graph. Now this is the structure may be different, the topology may be different for different nodes, but the operations that we are doing is basically same, right? So at every layer we are doing 2 operations, aggregation and then non-linearity. Okay, so we also have seen this equation. This is the main equation. So in order to compute the hidden state or the embedding, right, embedding of a particular node at depth k, you basically first aggregate all its neighbors embeddings, right? You take an average, right, and then you project it using this projection matrix WK. Similarly, your embedding, right, the embedding of the node V is also projected through BK, right, and then you add them, pass it through a nonlinearity, and that would give you the representation of this node at kth layer, right? And you start with how do you start? You start with either a 0 hot kind of encoding, or you start with a feature of the node. If the features are available, you can initialize the vector by the features. Okay, and then we have seen that we can also, I mean, since this formula is nice, you can make it a compact formulation using matrix forms, where you basically have 3 kinds of matrices. You have H, you have W, and you have A. Now this A matrix is basically a combination of your adjacency matrix and degree matrix, right? So yeah, so this compact representation is useful because ultimately you have to do matrix multiplications, right? And we have also seen that if it is a, if you want to tune everything with respect to a particular downstream task. For example, the task is node classification, right? You can define a loss, and the loss can be a simple cross entropy kind of loss, where, right, you have two labels, right, 0 and 1, and this is the label, and I mean this is the ground truth, and this is the label obtained from the classifier. Now, this classifier can be a simple, right, a feed forward network, a multi-layer perceptron type classifier, or this can be even a logistic regression as well. And this theta is the classifier. This theta is the parameter of the classifier, right? So once you get the embedding, for example, from this node, right, you pass it through a classifier and you get a loss, right? So this loss function is now propagated propagated through the entire network till the beginning, right? So then you basically you have to take the derivative with respect to theta, which is the parameter of the classifier, and with respect to the parameters which are used here, right? I mean the neural network parameters W and B. Okay. This is the idea. So now this is useful because this is also useful for an inductive setting, right? I mentioned what is inductive setting. In the inductive setting, so there are two kinds of machine learning methods. One is called transductive methods, other is an inductive method. In transductive method, you have access to the entire data set, but you know the label data of a few nodes, for example, and then you classify other nodes present in the graph. So you have access to the entire graph. It is not that the test set is unknown to you. The label is unknown, but the test set is not unknown to you. It is known. Whereas in inductive setting, and that's transductive. Now in inductive setting, you do not know if new nodes are coming in. I mean, when you train your model, right, you do not know the you do not know this new nodes which are going to come, right? So the idea is that if you use GCN kind of method, this has this capability to also infer the embedding of nodes which will come in the future, right? Why? Because let's say this purple node, right? So now this node was not present here. So you basically train your model, right? You know that you say you have two layers, layer 1, layer 2. You have W1, B1, and W2, B2. That is already that you have already learned, right? Now when the new node comes in, what you need to do, you basically need to get the computation graph for this particular node. So you get the computation graph. You know that okay, so this is U, X, Y, A, B, something like that. So you can then draw the computation graph, right? Something like that. Okay. Then, right? And then now you don't need to train anything, because you know that the first layer you have W1, B1, which you already got, and the second layer you have W2, B2, right? You just multiply accordingly, and then you get the representation. Okay. So therefore, it has this inductive capability. Okay. So now we will look at even more generic version of graph convolutional network called GraphSage. Now the idea behind GraphSage is basically same as GCN, right? But with a little difference here and there, right? But if you look at the paper, the original paper, they have also proved many things. For example, why this? So the major difference we'll discuss here between GCN and GraphSage is that sometimes GCN GCN sum all the the embeddings of the neighbors, right? It basically sums up the embeddings of the neighbors, whereas GraphSage tries to keep the embedding of the neighbors and the embedding of the original node, right, side by side without aggregating, right? There are some changes here and there, and we will discuss. So this is same for every node. We have this computation graph. Okay. Now, in order to compute the embedding of node V at layer K, what we have done so far in case of GCN, again, I am showing you the equation so that you understand, you remember. So try to memorize this equation, right, for the time being. So what it is essentially doing is that you are aggregating, right? You are basically somewhere taking the summation over all the neighbors of V, right? And then you average it. Okay, and then you similarly you get a projection from your projection of your own embedding, and then you again sum it up, right? When you basically sum them, right, what happens is that you do not have control on which part of the embedding is which part of the embedding corresponds to the corresponds to the node itself, and which part of the embedding corresponds to the neighbors, right? So the model might be confused. The model may want to give some extra weightage to the embedding of the own node, whereas little less weightage to the embedding of the neighbors, right? For example, some tasks, right? So in GraphSage, what they suggested is that instead of simple, instead of simple aggregation, right? What you do, you keep these two things separate, right? Now, this is the embedding of embedding of the neighbors, right? As you see here, u belongs to NV. NV is the neighbors of V. So for every neighboring node u, right, you have embedding. So say there are 5 neighbors, so you have 5 embeddings. Now you define some aggregation function. This aggregation function can be a summation, for example. If this is summation, then this is same as GCN. But this can be other types of, you can use other types of aggregation method. I will discuss some other types. So now this is one part, right, where you take the embeddings of your neighbors and you run some aggregation method, and then you get the some sort of combined representation, aggregated representation, right? And then you pass it through. You basically project it. So AK is something which you learn. Similarly, and this is same as earlier. This is your own embedding at the previous layer, right? And BK is the matrix, projection matrix. You project it, you get an embedding, right? So from here you get an aggregated embedding. From here you get a embedding of your own, projection embedding of your own. Then you see, so in the GCN, what we did, we took the sum, right? But here you see there is a comma. This comma indicates the concatenation. For example, this is the, so say this is the aggregated embedding of the neighbors, and this is the embedding of your own, right? And then you basically concatenate them, right? You are not aggregating, by the way. You are not summing them up. You are concatenating. So the good part about concatenation is that you can separate the two components, right? So that the model, so the next layer, for example, in the classification layer, for example, the model may want to give more weightage to this component rather than this component. Okay, and then when you concatenate, after concatenation, you pass it through a nonlinear and you are done. Okay. Now let's look at what are the aggregation method that you can use, right? So a simple aggregation is the one that we have discussed in this year, right? You sum them up and you normalize it by the number of neighbors. This is one aggregation function. Here, what you are doing, you are giving same weightage to all the neighbors, right? The weightage is 1 by NV. 1 upon NV is the weight of every neighbor. Right? It's a simple average. This is not a weighted average. Another aggregation method could be you do some pooling. Okay. For example, right? For example, you see that this is your say one. I'm just writing some numbers. These numbers are not that great, but this is useful. Say 1 0 1 1 2 2 1 0 0 1. These are 3 embeddings of your neighbors, right? What you can do max pool or mean pool or whatever. mean MEAN pool or MIN pool, right? Max pool, mean pool, whatever you want. So you column wise, you do max pool. Say for example, if you do max pool, it will return 2. If we do max pool here, it will return 2, 1, 1, and 1. Right? So this is some sort of element wise max pooling, mean pooling, right? On the embeddings of your neighbors, right? This is one approach. In fact, you can do even more sophisticated things. You can essentially, employ an RNN kind of model, say LSTM model, right? Now, what this LSTM model will do? Now, this is the LSTM model, for example, right? A simple RNN model. What will it will do? So let's say there are 3 neighbors. This is the input. This input is the embedding of neighbor 1. This is input of the neighbor 2, and this is the input. This is the embedding of neighbor 3, and then you get an aggregated representation here. So this is parameterized because LSTM has its own cost parameters. The issue here is that, what's the issue? The issue is that LSTM generally is used when you have a sequence, right? And it tries to capture the sequential nature of the data. But here you do not want that the model will learn that this is the first neighbor, this is the second neighbor, this is the third neighbor, because neighboring order doesn't make any sense. There is no ordering of neighbors, right? Neighbors are neighbors. There is no ordering of neighbors, right? So LSTM should not capture the ordering. LSTM will of course give you the some sort of aggregated embedding, but it should not capture this. So then what do you do? How do we let the LSTM model not to learn the ordering, right? So what you do, you basically run this LSTM model multiple times with a shuffling of the inputs, right? For example, say this is the embedding of neighbor A, this is neighbor B, this is neighbor C. Now you get some output. In the next iteration, you feed this B, then A, then C. The next iteration says C, right? A and B. So you shuffle the inputs and then you feed it to the different RNN cells, right? Multiple times. So you will get multiple aggregated outputs, and then you somehow concatenate them. I mean, you somehow aggregate them. You can take average or whatever. Average is the best option. So you see here in this equation. So this is your neighbors, and you do some shuffling. This pi indicating the shuffling. So you get some shuffled representation, and then you pass it to the LSTM. You get an aggregation. Okay, this is even more sophisticated because you are employing another round of nonlinearity, right? Another round of learnability into the model. Okay, so that's all. That's the difference. Now in the paper, I'm not going into details of that. In the paper, it was shown that if you use mean versus if you use pooling versus if you use LSTM, theoretically, what's the implication, right? Empirically as well as theoretically, what's the implication, right? And this is, although this looks like a very simple, modification on GCN, but it turns out to be really helpful because now you are talking about a generic way of aggregation, and you are also showing theoretical guarantee that which one is useful, which one is not useful in which setting, right? That's all. So this is graph Sage, and here also you can get a compact representation using matrix. So this is the kind of matrix that we have seen earlier. This is another way of also getting the compact representation where you break this D into D to the power minus half or D half, and then you get HK. Okay, so now these are the reading lists that you can go through. You can see that there are tutorials, nice tutorials on graph neural network, inductive bias. There's a paper on graph attention network we will discuss today. Okay, there are papers on age embedding, which we have not discussed in the lecture, right? There are papers of how we can let the graph neural network aware of the position of the node, right? There are approaches where it was shown that how spectral approach and GNN kind of approaches can have analogous output, right? And how you can use even spectral theory in graph neural network. This is a very interesting paper. This is on geometric deep learning, which also talks about embeddings on the other space, right? Not only Euclidean space, but also hyperbolic space, for example. Right? There is another GNN paper called GNN Explorer, GNN Explainer, which basically tries to explain why this GNN method is really useful in practice. Okay. So now we move to the last topic of this chapter, which is called graph attention, right? If you do not know what is attention, you can go back and see some of the basic materials on attention. But basically, the idea is that when you aggregate in the context of graph, right? When you aggregate the embeddings of your neighbors, what we have done so far, we have, let's say the aggregation operation is simple as sum, right? Like this. What we have done, we have simply taken the average, right? Now, when you take the average, we basically give equal weightage to to every neighbor. Okay, but it may happen that some neighbors are more useful than the other neighbors to generate the embedding of the node, of the given node, right? Now, how do you know that which neighbor is more useful, which neighbor is not that useful? A simple way to look at it is that if you have, say, weights in the edges, right? Weights associated with the edges, right? These weights basically indicate different importance or impact, right? Now you can easily say that, okay, if the graph is weighted, right, I will do weighted average. Why do we need attention? But you can do a weighted average, but there is no learning happening. You mean that it may also happen that although an edge has higher weight, right, that edge may not contribute to the final classification task, because ultimately everything is dependent on the way everything is dependent on the downstream classification, right? It may happen that even if the weight is high, it is not that useful in the final classification, because this weight is generated from a different phenomenon. For example, say in case of user interaction network, the weight is say number of interactions that has happened between you and your friend. Now remember one thing. Let's take an example, right? Let's say I have 5 neighbors, I have 5 friends, and 3 of my friends are my classmates. And this is obvious that I interact with those 3 friends quite regularly. Therefore, the weights of those edges would be higher compared to the other 2 friends who are not my classmates, but who are who say I meet not that frequently. Those 2 friends may not have similar interest like me, right? But at some with respect to some aspect, for example, both of us are fan of Barcelona, for example, or both of us are fan of Maradona, for example, right? Both of us are fan of say Sachin Tendulkar, for example, right? So when we take these weights, right? So your weight will tell you that you should focus more on these 3 friends who are your classmates, but your classmates and your embeddings are same, because you have same sort of activities every day. You should also look at those 2 friends which are different from the other friends, and their impacts would also get reflected on your embedding, right? So in the final classification task, these 3 friends who are you are interacting quite often, they may not contribute more compared to these 2 friends who you do not interact frequently, right? So there should be a learning paradigm. There should be a learning approach by which you can determine which weight is useful, which weight is not that useful for a particular task. Okay. So far we have considered that the impact of every neighbor is same, which is 1 by n, kind of uniform impact. right? But you can define this alpha uv. So alpha uv is the impact of node u on node v. You are, remember, you are generating the embedding of v, and u is one of the neighbors. So you want to understand the impact of node u on node v. Okay, and right now this is called attention. You basically want to understand how much attention you should actually give, right, to one of your neighbors, which is u in this case. How much attention you want to give to another neighbor, say w, right? And this attention is something that we will learn automatically. This alpha value is something that we will learn automatically. Okay, so right, another learning module, another set of parameters, but who cares, right? Let's increase the number of parameters exponentially, for example. Okay, so that's fine. So so in order to compute this attention alpha vu, what you do, you basically come up with some sort of attention, you know, some sort of this a is a function. Okay, I'll tell you what are the possible functions that you can use. Remember, what is our task? Our task is to compute the attention of every pair of nodes between every pair of node and its neighbors. Okay, so in order to compute this, we need a function a. So what does it do? It basically takes into account the embedding of your the embedding of your neighbor at the, of course, at the previous layer, right? And your embedding, again you pass it through some sort of projections. In wk, these are wk is a matrix, right? You multiply the matrix with a vector, right? So right, this will give you a vector. This will also give you a vector, right? And then you run this function a. This will give you another vector, right? Right now, this e vu, this can be a vector, or this can also be a scalar, depending on how you define a, right? So this evu is called the attention coefficient, right? This is called attention coefficient. So this attention coefficient may not be normalized. What you want to do, you want to normalize this. So say this is v, and these are your u's. So this is u1, u2, and u3. So you will get ev u1, you will get ev u2, you will get ev u3, right? Now these weights, these are also weights, right? Remember, these weights have been generated based on this projection wk, and wk is something that you do not know, that is a trainable parameter, trainable matrix, right? Now these weights are not bounded between 0 to 1, right? So you want to bound it because ultimately you want that, okay, everything looks like a probability, right? What you can do, you can then you can basically sum them up, and then you normalize it. Basically, this is basically a softmax kind of operation, right? So you see exponential of, say, the final attention value between vu, the one that we want to compute, right? This will be generated from the exponential of this one by the sum of this exponential across over all the neighbors. Okay, right? Now this is your attention, right? Now when you aggregate, you remember we have done aggregation, right? When you aggregate, what we have gotten so far. So we remember that, let me go back, right? Let's say here, right? So we had this aggregation method, right? We sum them up. So here what you do, instead of simply taking this, what you do, you basically multiply this by alpha vu, Okay, you can ignore this one. Okay, now this is what? This is basically, now this is a weighted average, because remember alpha value, all these alphas, right? These range, they range between 0 to 1, and the sum of them should be 1, right? Because it's a probability, right? So therefore this is weighted average, right? So right now this attention, this A, right, which we have not discussed, right? This A you can compute in different ways. For example, now this is, remember, this is I mean how do you decide which function you should use, right? Now this is completely agnostic to the neighbors. For example, what you can do, you can simply employ another neural network, a single layer neural network, for example, right? If you just use a feed forward, single layer feed forward, these are the inputs, right? You squeeze it using neural network and you get an output, right? If you use single layer neural network, then alpha will also have parameters. So A will also have parameters. So A will have parameters. You have W's which you want to learn, right? So you have many parameters. Okay. And of course, when you train the model, it will basically, the model will be trained in an end-to-end fashion. So all these parameters will be useful in order to compute the gradient, right? You will take the gradient with respect to each of these parameters separately. Now there was a paper, in this paper, right? It's ICLR 2018. It said that we can also make it little sophisticated by using something called multi-head attention. Now the multi-head attention is very popular in NLP, right? What it basically does is that so far we have what we have done. We basically took a pair of nodes, right? We pass it through some projection, and we get some attention vector, right? Attention value, attention vector, whatever, right? So what they said is that, look, multi-head attention can be done in two ways. One way is that instead of using one projection, you can now use 8 projections, for example. Okay, and all these 8 projections are trainable, learnable, and so one projection means one matrix, WK, right, that you want to compute. So you can use 8 different projections and then you aggregate them. Well, this is one way of doing multi-head attention. Another way of doing is that, let's say the dimension of your embedding is 8 or say 16, right? What you do, you break the embedding into 2 parts, 8, 8. Okay, so then you employ 2 projections. So one will project the one part of the embedding, other will project the other part of the embedding, right? So you get projections and you then concatenate. So if you have 64, you break into 4 parts, for example. You basically pass each projection, each part through a projection, then you aggregate all the projections, right? Sorry, you basically concatenate all the projections. Or you take 64 dimension, you have different projections of size 64 cross 64, you pass it, right, and then you aggregate them. You just sum them up, whatever is there, right? It turned out to be useful to stabilize the process, because otherwise it gets fluctuated a lot, right? So if you do this, it will get stabilized, and that would also useful in your learning process. So that's all. That's pretty much about GAT. And it turned out to be really effective empirically as well. You see here, this is an example taken from a paper where the application was node classification, and you had whole bunch of methods, multi-layer perceptron, right, simple approaches, linear projection, deep work kind of methods, right? You have GCN, and you see that GAT performs significantly better than even GCN, and of course much better than deep work kind of methods, right? So and this is on a citation, I think Quora citation network. Okay, and you see the TSP plot. This is the visualization of the the output obtained from GAT. You see that nodes are highly separated. Okay. Okay, so this is pretty much about GAT. There are many advanced methods that have been published, that have been published regularly, right? You keep track of the progress of graph neural network. This is a very hot topic these days in graphs, right? You can look at, you can regularly track conferences like NeurIPS, KDD, right? ICML, ICLR, ICDM, these kind of conferences where you get more this kind of methods. With this, I would like to stop. I hope you enjoyed the lecture, and I also hope that the book is of some use to you. And yeah, see you. Thanks. Bye.